Alright guys, in this first problem we have a beam of particles that is entering a magnetic field that has two regions. Region 1, the particles stay straight, and then region 2, the particles do some kind of curving motion. So the first thing you're asked is to figure out how do these particles stay straight right here in this region. So the first thing you need to look at is what is the direction of the magnetic force. You're told that you have a positive particle and that there's a magnetic force that goes through here and an electric force. So the first thing you have to take a look at is your right hand rule. Your thumb is the velocity of the particle. Your fingers are going into the paper. So you'll put the fingers toward the paper and your palm will point up. So what that says is that the magnetic force should be pointing up. So the particles should start to curve up in this direction. But they don't, and that's because there is an electric force that the particles experience too. Now to figure out the direction of the electric force, draw yourself a free body diagram of the particle. So we have a magnetic force going up, and we have, since it's not moving up, since it's staying straight, we must have something equaling out that magnetic force, which is an electric force. And since you know that positive charged particles go with the field, then your electric field is going to point down. Alright, the next thing it asks is to calculate the speed of the particles as they pass through region 1. So, if you go back to your free body diagram, you have magnetic force going up, you have electric force going down, and the thing is in equilibrium, so that means the magnetic force must equal your electric force. You know your magnetic force is equal to QVB, and your electric force is equal to QE. And you're asked to figure out what is this velocity right there. Now you should notice that both of these have a Q on it. That Q is the same, so you can cancel it out if you want to. And your velocity ends up becoming your electric field divided by your magnetic field. So your electric field is given to you as 4,800 newtons per coulomb, and your magnetic field is given to you as 0.12 Tesla, and 4,800 divided by 0.12 is going to be 40,000 meters per second. Alright, next thing you're told, particles pass straight through inner region 2 where there's no electric field and the magnetic field is the same, and it asks you to figure out what the radius of it is. So if you go back to our first picture, and our particles came in here straight, and if you look at your right hand rule, field's going into the paper, thumb is pointing to the right, so that means the magnetic force will be up, which means that they will curve like that, where the magnetic force is constantly pointing to the center of the curve. And since this magnetic force is pointing to the center of a curve and it's a circle, that means it's centripetal. So I can say that my magnetic force is equal to a centripetal force, where the magnetic force is QVB, and the centripetal force is equal to mv squared divided by r. So you want to solve for radius, so let's rearrange this for radius. Multiply each side by r, which equals QVB. Let's scratch that. I always like to do a cancel out first. I usually do this in my head, but this velocity here and one of these squares there will cancel out. So your r will equal mv over qv. So you plug in the values that you know. Your mass is given to you as 6.68 times 10 to the negative 26 kilograms. I think it's a strontium atom. Your velocity, we found earlier, 4 times 10 to the 5th meters per second. That's 40,000. Divided by your charge is 3.2 times 10 to the negative 19th coulombs. Again, it's a strontium atom, it's in group 2, it's a +2 charge. And your radius, your magnetic field is 0.12 Tesla. So multiply the top, divide by the bottom, and you'll find that your radius should be 0.07 meters, or 0.069 or 68 or something like that, but I remember it's 0.07. Alright, Look on the back side. It says, within the beam there are particles moving slower than the speed you calculated in 1. In what direction is the net initial force on these particles as they enter region 1? Now, region 1 is the part that has both the magnetic field and the electric field. So if you look at your free body diagram, again, it always goes back to the free body diagram. You should be drawing FBDs as much as possible. So you have the magnetic force going up, and then we have the electric force going down. Now, the electric force is equal to QE. It is just dependent upon the field and the charge of the particle. But the magnetic force is equal to QVB. It's equal to the charge of the particle, the field, and the velocity. So the greater your velocity is, the greater the magnetic force is. So if a particle enters this region with a speed slower than region 1, that means that this right here goes down, or drops. It doesn't go down, just it gets less, which means that this whole side here will become less, which means that my electric force will actually become greater than my magnetic force, and the net direction of these will be toward the bottom of the page. Alright, and then in part D, it says a particle of the same mass and speed as in A2, that means just the strontium atom, but with a charge of negative 3.2 times 10 to the negative 90 coulombs, enters region 1. The following diagram sketch it, so let's do a little diagram right quick. We have our separation, we got our field, and then we're entering in. Now, so in region 1, you have to look at your right-hand rule. Since the charge is now negative, we know that the electric field is still pointing down. Since the charge is negative, our electric force now will point up. But if you look at your magnetic force, your direction of your particle is to the right, your field is going down, so your palm's pointing up, but this is a negative charge. Remember, negative charges act opposite, so that means that, this is the electric field, that your magnetic field will now be pointing down. So if you have a negative charge, you can still be in equilibrium with both the electric and magnetic field. Just the negative just switches the directions of the forces around a little bit. Now, since when it enters region 2, where there's no electric field, then this whole electric field here goes away, so your net force for your particle is pointing down, so we're going to come through here straight, and then we're going to curve down and have a circular motion. And that's how to do this problem.